Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Josh Kramlick.
Thank you, William. And thanks everyone for joining us today for this installment of the Tech to Tech series. My name is Josh Kramlick, and I'm the Americas Sales Manager for KYZEN Corporation. What do we mean by soil management? In production parts cleaning, our focus is on removing soils or unwanted contaminants from the parts or components. However, once those soils reside in the system, we have a new challenge, which we'll refer to as soil management. Before we get into the soil management toolbox, however, there are a few key considerations we should discuss. First, cleaning chemistry. Whether we're using a solvent or an aqueous-based system will have a substantial influence on the tools ahead. Second would be the process equipment, whether we're using spray and air, ultrasonic immersion, or perhaps agitated immersion. And probably most importantly, the type of soils. And we'll discuss those soils in two key categories. The first will be insoluble contaminants, particles or manufacturing debris. This is primarily going to be metal swarf from machining processes or residual abrasives from polishing, grinding, and perhaps lapping. And then we have soluble contaminants, where we're talking about ionic compounds, organic and inorganic residues, oxidation, and corrosion. Importantly, the selection of the cleaning process and chemistry in some cases determines whether contaminants are soluble or insoluble. For example, in a solvent-based cleaning process, oxidation and corrosion would be insoluble. However, in the appropriately specified aqueous process, those would be easily solubilized. So let's talk about the primary soil management methods. This is our toolbox that we have to work with. The first is filtration, the mechanical capture of insoluble contaminants. And this primarily we talk about strainers, bagger cartridge filters, magnetic filters, centrifugal filtration, or membrane separation in the case of emulsified contaminants. Much like your morning coffee, the good stuff will pass through and the grounds are retained in the filter. Second, distillation, we're talking about separation of higher boiling point dissolved soils, or as in the example on the lower left, getting the good alcohol away from the stuff that will blind you. Specific gravity, separation of non-mixing phases, as demonstrated by the B52s in the upper right. And fourth, neutralization is the mitigation of acid or base accumulation in a system, and almost always required after a round of B52s. So before we go further, we should talk about how you assess cleanliness. In many cases, it's purely visual. We're looking for particles, either under magnification or not, or possibly residues or discoloration. Particle count and classification is really a key measure in automotive applications, where customers are compliant with ISO 16232 or the VDA 19 standards. This is often referred to as millipore testing. Surface energy, whether you're measuring contact angle or using dyne pen testing to assess the residual organics on a part. Perhaps SEM EDX, where we're looking at elemental or compositional analysis. Other analytical methods, including gas chromatography, mass spectrometry, Fourier transform infrared spectrometry, ion chromatography, and in some cases, we have regulatory compliance concerns, such as cytotoxicity. So filtration systems should be built around the cleanliness specification. Let's start with an example. Let's consider that the largest acceptable particle size is 150 microns. The first option would be to utilize a 50 micron nominal cartridge filter. The second option might be to look at a 100 micron absolute filter. The important thing to note is the capture fraction of nominal filters can vary wildly. A 100 micron absolute filter cartridge will guarantee that zero particles greater than 100 microns are able to pass through. However, there's a significant cost differential between those two types of filters. We should also consider the amount of particle contamination and expected change frequency for the filters. One way to address this would be to consider progressive filtration. Progressive filtration might include an example of putting a 150 micron bag filter above the 50 micron or 100 micron filter cartridge. Operational concerns. Can I afford to shut down the machine for filter changes? If the answer is no, then parallel filtration with isolation valves is necessary. We also have to consider material selection and compatibility. The O-ring seals and the material of the filter construction itself must be considered and must be compatible with the chemistry that you're using. And of course, in all of this, it's important to think about the specification of the pump flow rates and pressures, especially when looking at progressive or parallel filtration systems. An important note is that in the submicron particle range, microfiltration and ultrafiltration systems may be much more complex than the examples here. Distillation considerations. Very important note is that the boiling point typically increases with soil loading. The impact of this could be that with higher boiling point contaminants, if we increase the distillation process temperature, those will survive the distillation, or we could have incomplete distillation and higher solvent consumption if we maintain the set point. Soil boiling points may be near to that of the base cleaning solvent. We had a recent example where a customer was pre-cleaning the parts with mineral spirits in a vacuum vapor degreasing system with modified alcohol. In this case, depending on the grade of mineral spirits, you have the potential for some co-distillation. Important to note that cleaning solvents are designed to have good thermal stability, however, the soils may not. Contaminants in soils may oxidize, resulting in visual changes in the solvent. But it's important to ask whether this will impact cleaning efficacy, and we'll come back to that a bit later. Using specific gravity in the method of oil separation. So there are numerous types of separation systems, such as disc or belt skimmers, coalescers, and centrifugal systems, which are more rare because of their cost. Disc or belt skimmers are relatively low cost, but need to be specified appropriately, because as you can imagine, a 1-inch belt skimmer on a 500-gallon tank might not be very effective. Coalescers tend to be much more effective, either using plates or media systems, but they also add challenges for waste retention and system cleanup. Important in all of these are the consideration of temperature and viscosity. A higher temperature aqueous process will lead to lower viscosity oils and less effective skimming. However, if a coalescing system is properly specified, adequate volume and residence time will still allow for good separation. Let's talk about which technologies are included in a typical aqueous cleaning system. Filtration is usually employed in recirculated cleaning systems, though we do certainly have some examples where it's not. And also where filtration is incorporated, it's frequently possible to identify opportunities for improvement. Specific gravity in the oil separator on the left of the image. This only works if the chemistries used are designed to split out these oils. If we're using emulsifying chemistries, they may require membrane separation. Neutralization may be required in any process where strong alkaline or acid chemistries are employed. It's important to consider here, we do not want these process chemistries to ultimately become a contaminant that we're managing downstream. What about soil management and vapor degreasing? Filtration, quite frequently used, especially when degreasing and particle contamination are both of concern. Specific gravity, when water separation becomes important to make sure we remove that from the system and eliminate risk of corrosion. Distillation, most systems incorporate integrated or ancillary units for continuous solvent distillation. And those that don't, a manual boil down can be used, which is effectively entails using the boiling sump as its own simplified still. Here are two examples of distillation and vapor degreasing systems. The left would be integrated. On the right would be an ancillary add-on system like the KYZEN Capture. Important to note that the functionality is basically the same in those. However, it's wise to know that ancillary and add-on systems are available. Let's talk about soil management in vacuum vapor degreasing systems. Filtration is universally employed in the systems that we work with. Specific gravity also universally employed in a water separation following the condenser. Distillation systems are integrated with the process to continuously distill solvent. It's important to note that the schematic here does not represent all vacuum vapor degreasing configurations, and the exact handling of the solvent from the still may be different. A final note on these is neutralization is a common requirement here, noting that any place we're bringing water or chlorinated or possibly sulfonated oils into the system could result in corrosion or contamination. So how do we measure soil loading, and how do we use it to manage bath life? One example would be fine filtration. So we use a gravimetric analysis of neutral buoyant suspended particles in a bath sample. For example, here we might extract a liter of bath solution, filter it, and find that we retained 2 milligrams of solids. In that case, we would have a 0.2% soil loading. NVR method is probably most common in the work that KYZEN does, where we're heating a known sample to drive off volatile compounds, and the exact profiles of those are application specific. Aqueous electronics cleaning applications, for example, where we're removing reflowed flux residues, may have limits of anywhere from 0.5 to 5% NVR. Typical aqueous metals cleaning applications, however, could be as high as 10 to 15% soil loading before we lose cleaning efficacy. Additionally, we have the opportunity of using advanced analytical methods such as gas chromatography or mass spectrometry or FTIR to analyze the compounds that are carried over through the distillation process. So a few miscellaneous considerations. Water quality. City water brought into an aqueous system can absolutely contribute to scale and deposits around the wash chamber. Foam in applications such as flux cleaning, the soils can contribute to foaming issues, and then this becomes a soil that also needs to be managed. Another example in industrial applications would be removing any stearates in buffing or polishing compounds, which also tend to increase the foaming. Your cleaning supplier will likely offer solutions that are designed to clean the systems completely prior to recharging. And finally, here, system and tank design. Solids contamination must be able to be pulled into the filtration system. This means adequate suction and careful consideration of port locations in the tank. We have numerous customer examples where solids contamination lays on the bottom of the tank and perhaps on an ultrasonic radiating surface, and that soil continues to degrade and may reduce in particle size and therefore escape the filtration system. So in conclusion, cleanliness specification and assessment should really drive all aspects of the cleaning system design and the incorporated soil management. Filtration is often an overlooked complexity in the design and management of a cleaning process and system. Bath life is not deterministic. The requirements of individual cleaning processes will influence acceptable soil loading levels for every different application. And most importantly, everything you put into your process will influence what comes out of it. So we'll wrap up with a few frequently asked questions here. First, how do I determine acceptable bath life? Again, this is very application specific, and depending on your cleanliness criteria and your method of assessment, your cleaning chemistry supplier will likely be happy to work with you to determine the appropriate criteria for your specific application. Question 2, why is the solvent in my vacuum vapor degreaser darker in color even after I run the full boil down? The answer to this question is that solvents and soils will oxidize and discolor, but it does not necessarily mean that the cleaning efficacy is lost. For example here, if your main criteria for cleanliness is a particle analysis, a darker solvent is not likely going to have any impact on you. Question 3, what type of water should I use in my cleaning system? Water quality is always a major concern. In most cases, we recommend using at least RO water to reduce the compounding agents that can interact with the soils and the chosen chemistry. And question 4, Can I change my filters in my cleaning process to improve cleanliness? Potentially, yes, but note the differences in performance of different filter brands, the differences in nominal versus absolute filtration, and of course, the impact on the pump performance in the system. With that, I would like to hand it back to William, and thank you again for joining us today.
Thanks, Josh. And thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further, or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@KYZEN.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.